Greetings, A-level chemists. Here we're going to have a look at some electrochemistry, or redox 2 as it's sometimes called, and we're looking at it under the scope of predicting reactions. So a student adds an excess of solid iron to a solution containing VO2 plus ions. During the reaction, the solution's colour changes in the sequence blue, green, violet. So using the standard electrode potentials in the table, we've got to explain why we get these colour changes. Okay, classic question. So first thing I'm thinking is, let's have a look at VO2 plus. So knowing our oxidation states, oxide is always -2 and there are 2 of them. So we've got 4 negative charges. We've got an overall plus charge on the compound iron. So what is the charge on the vanadium? It is going to be +5, because 5 take away 4 gives us +1 overall. So that's vanadium in the +5 oxidation state, okay? So then, what I'm thinking is, a good way of answering these questions is actually circling the components we have from the question, okay? So we're adding an excess of solid iron. So let's find iron in this redox table. So there it is, okay? And then we're adding that to a solution containing VO2 plus iron, so vanadium 5 plus. So now I'm searching for vanadium 5. Be really careful about the formula here. It's there. There's vanadium 5 plus, okay? So then think about what's going to happen. Now, the most negative one, so the iron is going to be oxidized, and the VO2 plus, or the vanadium 5 plus, is going to be reduced. Okay, we can give equations for this as well. Okay, so let's just break this down into the oxidation process and the reduction process. So the oxidation process is going to be Fe to Fe2 plus 2 electrons. And if you want to do it this way, what you can do is you can say that Eox is equal to not minus 0.44, because that's given as the reduction potential. So we're going to quote this as the oxidation potential, so that's going to be plus 0.44 because we're going from right to left. So this is going to be plus 0.44. And then for the reduction, we've got VO2 plus 2H plus an electron, and that goes to VO2 plus H2O. And there, from our oxidation states, we know that O is 2 minus. So therefore, V has to be +4 to give us the overall charge of 2 plus on this vanadium compound. Okay, so we know that this is vanadium 5 plus. And if we remember the colors, +5, +4, +3, +2, it's you better get vanadium. And this tells us of the color changes that we see, okay? Now, you better get vanadium as a way of remembering it. What colors did those refer to? Well, those colors refer to yellow. So the Y stands for yellow. The B in beta stands for blue, the G stands for green, and the V in vanadium stands for violet. So associate those oxidation states of vanadium with you better get vanadium, where the beginning of each word is the color it's referring to. So the Y stands for yellow, the B stands for blue, G stands for green, and the V stands for violet. So when we have vanadium in the +5 oxidation state, it is yellow. And when it's in the +4 oxidation state, it's going to blue. Now, we actually haven't accounted for why this occurs, but we'll do that because E red is given to me, or the reduction potential is given to me as +1.00. So this is going to be +1.00. Now, for the next bit, how do we work out what E cell is? Well, there are many ways to skin a cat. We can say that E cell is equal to E red minus E ox. Okay, this is one way of doing it. This is one way of doing it, okay? So let's have a look. Now, if you do it this way, what you don't want to do is use those reduction potentials that we just worked out in the top right, okay? Because what we've done there is we've changed the sign. We want to say that E cell, we're going to keep all the values or the signs the same here, I'm going to say. So E red is plus 1.00 minus E ox, and the oxidized potential is minus 0.44. We're going to leave that sign in, and then E cell equals plus 1.44 volts, positive, therefore feasible. Okay, so that's one way of doing it. The other way of doing it is once we've already converted E ox to the positive value, we can say that E cell, if you do it this way, if you flip the signs, is equal to E ox plus E red. So E cell is equal to plus 0.44 plus 1.00. So E cell is equal to plus 1.44 volts. Whatever works, okay? Whatever works. I normally use the top right, but you can use this as well, okay? All right, let's go. So we've justified the first color change, yellow to blue, feasible because E cell is positive. Okay, so then where do we go next? So let's start numbering these guys. So that's number 1, and let's say this is number 2, and let's partition this a bit. Okay. We're just going to divide this up. Cool. All right, we are in business. Let's go. All right. So what do we have next? So now think about what we have in the vessel. So now we have VO2 plus, okay? And let's look at our redox table. We have VO2 plus and we have some solid iron. Okay, we still have some solid iron, so we still have a lump of iron, but now we have VO2 plus. And then what I'm thinking, the VO2 plus that I have, can that be reduced further by the iron? So let's have a look. So can we get VO2 plus to be reduced to V3 plus? Question mark. And let's go through this. So the oxidation is still going to be Fe to Fe2 plus 2 electrons. And the reduction this time potentially could be VO2 plus 2 protons plus an electron goes to V3 plus H2O. Okay, so let's see if that's feasible. So if we do E cell is equal to E red minus E ox. So let's just put our reduction here. So that's our reduction. So E cell is given as E ox, which is minus 0.44, and E red is this value here, which is plus 0.34. So what do we get here? Let's process this. So we get a value of plus 0.78 volts, so feasible as positive. And think about the color change. We're going from plus 4, so vanadium in the plus 4 oxidation state, which is blue. And we're going to vanadium in the plus 3 oxidation state, which is green. So we've accounted for the color change to blue. We've accounted for the color change to green. Does it go violet? I mean, presumably yes, or they wouldn't be asking the question. So let's think about what's happening now. So now we've generated vanadium 3 plus. Here's vanadium 3 plus. And now I go to this redox system where the V3 plus could potentially be reduced to V2 plus. And does that happen with the excess iron that we have? So now what I'm thinking, can I go from V3 plus to V2 plus? Question mark. Well, the oxidation for the iron is going to be Fe to Fe2 plus 2 electrons, and the reduction is going to be V3 plus an electron goes to V2 plus. Okay, is this feasible? Well, let's work out what E cell is. So E cell for this would be the oxidation and the reduction. So the reduction is this value, minus 0.26, minus the oxidation, which is minus 0.44. So it looks like we're going to get a plus value, so feasible. Okay, so let's work out what we get. So I get a value of plus 0.18 volts here. So that is definitely feasible. And if we go back to the oxidation numbers, if I generate V2 plus, that will be violet. So we've accounted for the color change from blue to green to violet, sorted. Okay, so I guess the next question is, why don't we generate vanadium metal? I know it's not asked here, but why don't we generate vanadium metal? Well, what can we do? Let's rationalize this and get a different color. Let's go for that color. So now we've got vanadium 2 plus here. Why doesn't the vanadium 2 plus get reduced to vanadium metal by the excess iron that we have? Because if we were to calculate E cell for that reaction, would be the reduction, which is minus 1.18, minus 0.44. So E cell would be a negative value. And we get a value of minus 0.74 volts, so not feasible. So you can rationalize it through E cell values, okay? And I guess if we want to put words, that we could say that iron is not a strong enough reducing agent to reduce V2 plus 2 V metal. Okay, thank you for watching. Hope that was helpful. Ta-ta.